Kb, a nitrogenous base example. The first part of this lesson is a bit of a story and some context, which could have some information that will benefit you outside of chemistry. If not, whatever. So, with no further ado, if you're traveling to a third world country, before you go there, you must see a travel clinic somewhere in Toronto and find out what medication or vaccinations or other pills you need to take. A couple years back, I went to Cambodia, and the travel doctor said, you're going to Cambodia, there's jungles there, there's different types of mosquitoes that carry malaria. I need to give you malaria pills that you take every day so that the chance of malaria getting a foothold in your body is almost zero. So any of these countries have a high prevalence of malaria. If you're going there, you're visiting, you'll get the parasite living in your body through a mosquito bite. Mosquito injects sedative into your skin. You don't feel anything, although that's what you might react to later on. It takes blood into its body, and then at the same time too, it leaves behind a parasite called Plasmodium vivax. And that parasite, as time goes on, will live in your body. It grows in the liver, it goes into the red blood cells, and then it bursts out. And when it bursts out, it causes a huge flare-up of malaria. People feel terrible, they're bedridden, a lot of people pass away from it. Mosquitoes bite you again, they take it up and then pass it on to somebody else. So Plasmodium vivax uses your body and the mosquito's body to complete its life cycle. So it's dependent on two different hosts at different points in time. Malaria currently is responsible for 2% of deaths worldwide. And it wasn't until the 1600s that there was some actual treatment for this whole thing. So basically it worked like this. We were going to an area that had a high risk for malaria. This is the border between Thailand and Cambodia, and you have to walk across the border. There's standing water where mosquitoes can breed, and only local trucks are allowed back and forth. On the top of the truck here, it's a whole massive amount of styrofoam containers. I know it looks a little bit like cocaine. It is not. It's all styrofoam takeout containers. So once we were getting close to that area, about 2 days in advance, we started taking medication called Malarone, and it was a preventive medication that's taken to disrupt the life cycle of the Plasmodium vivax. And by having this life cycle disrupted, even if you're bitten and infected, the protist isn't able to do anything with that, and it ceases to exist. So the question might be, well, why are you going to a place with malaria? Well, when I was about 8, I saw a documentary on a religious site called Angkor Wat in northern Cambodia, and since then it's someplace that I've wanted to go to. So we flew into Bangkok and then took a bus to the border. The border, you saw the picture there before, standing water, all that kind of stuff. We'd taken our malaria medication, everything was fine, and we continued on a unpaved highway to Siem Reap. This is the unpaved highway. We found out later that Bangkok Airways is paying, or thought to be paying, the government not to pave the road so that people will fly instead of take the bus. We took the bus one way. We already had tickets to fly back. And that turned out to be a very good decision. This road here has potholes in it. We got a flat tire. We stopped at a gas station. And yes, those are half liters of gas you can buy, or 5-liter containers of gas as well that you can buy. It's very, very different compared to gas stations you see in North America. Finally, though, we got to Angkor Wat. Angkor Wat is the world's largest religious complex. The amount of money it took to build these towers and the whole sprawling complex was thought to be the factor that bankrupted the Khmer Empire a couple hundred years ago. And after that, the empire fell into ruins and everything there was sort of lost to the general world knowledge, although people still continue to live in that area. The stairs that you can sort of see here are about 60 or 70 degrees high. It's very, very steep stairs, about twice the steepness of what's in your house. And they're high enough that if you were to fall, you would probably miss most steps and just hit the bottom. And the idea there is that the person felt that as you're climbing up, you should feel like you're climbing up towards heaven. Place is huge, absorbs a whole lot of visitors, a lot of very interesting different temples and areas. You might have seen this tree before. This is a temple there called Tafram, where the trees have become embedded with the stone structure. It's all intertwined, and as much as we had to take medication to go there, Malarone, to make sure we're safe and everything, there's mosquitoes and whatnot, and some massive spiders. It was absolutely stunning to see this level of nature taking over civilization, and to what extent. The point now is that trees like this and the one here which you might have seen in the older movie Tomb Raider, have completely engulfed the structure to the point where the tree is holding up the building and the building is also holding up the tree, a man-made nature symbiotic relationship, if you will. And I think the first time in my life I've kind of been afraid of a plant. They're really, really big and really imposing. Now, why do we say all that? Well, if you went to this kind of situation or this kind of forest a couple hundred years ago and you got malaria, the best hope for treatment would be this molecule called quinine. No surprise, quinine is a base in water. Why is that relevant? Well, it's relevant because it treats malaria, which gives us the context. And the second thing is it's relevant because it allows us to calculate the pH of the solution. So while you're grabbing a piece of paper and while you're sorting all that out, one other thing I'd like to say, if you get sick in a third world country, and unfortunately when I came back from Cambodia, I ended up getting sick the day I got back to Canada, it made me appreciate the length of vacation I had, because had I been there longer, I would have been sick overseas. However, it wouldn't have been that bad. And the reason why is that before I left, I got the vaccinations, so I knew what illnesses I didn't have. And the second thing was I purchased medical insurance. In Canada, we have quote unquote free medical care. I know 40% of your tax covers that, but that ensures that whenever you get sick, wherever you get sick in Canada, you're covered because you're supposed to be here and this is your country and this is where you live and you pay tax and all those kind of things. So we're totally safe in Canada. But when we go to a third world country or even we go to the States, our medical coverage doesn't cover us anymore. So if you get sick there, if you're hospitalized, if you break your leg, you're on the hook for the bill for that. And you could end up in that situation being at a second-rate or third-rate hospital or clinic. If you know you have to pay for it yourself, you may not look for the best treatment. Travel insurance companies make sure that you're put up in a hospital that has a similar standard of medicine as you would expect to find in North America, or in Canada, I should say. Now, all that kind of stuff, hopefully that helps you out someday. If you're traveling, get a vaccination, get medical insurance, because the downside of those things don't outweigh the small amount of money those things do cost. Anyways, back to quinine. So with quinine, we have quinine acting as a base in water. So on your paper that you have in front of you, we're going to look at determining the pH of a solution of quinine that has a Kb of 3.3 times 10 to the negative 8 and a concentration of 0.1 moles per liter. Before we go any further, we'll take a quick look at our structure here. This structure is the type of structure we'll be dealing with in our organic chemistry unit, which is the next unit we have. We'll finish the course with electrochem. What we have here are several ring structures of benzene. We have nitrogens. We have a hydroxyl group, not to be confused with hydroxide, that is connected through a charge. This is covalently bonded. We see that we have some type of three-dimensional structure here, reminiscent of our atomic structure unit. And a lot of those concepts we came across before, the sigma bond, the pi bond, all that stuff is going to be coming back. Now, taking a look at the question itself. Well, the first thing we do anytime we have a question is to figure out what we know, set up a strategy, find our direction, and start working towards that. In this case here, what do we know? Well, we're given the Kb, we're given the concentration, and we're told as well that we have a pH we need to find, and we're dealing with hydroxide. So our first step then is to write an equation. Notice that we're dealing with quinine, and we don't care about the chemical formula. There's no sense to write all the protons and everything else we have. We'll call quinine Q. We know it's aqueous, and we know that it's mixing with water. This gives us a protonated quinine and hydroxide. We're already told we're dealing with a Kb, so we know we're going to produce a base as a consequence. We'll start making our ice table. The question gives us our 0.0017 moles per liter as our initial concentration of quinine. We can also safely assume we don't have a protonated quinine to begin with, and we can assume the autoionization of water for hydroxide is 0, or there isn't any hydroxide to begin with. The change has to be negative on this side because we can't possibly go lower than 0, so this side must lose, this side here must gain as quinine is protonated. At equilibrium, our values are going to be 0.0017 minus x, a plus x, and another plus x. Our Kb expression is products over reactants, and this should look eerily familiar to our Ka example, our KSP examples, and the stuff we've seen previously where we have this x squared emerging. In this case here, we have the minus x. Well, we have the 100 rule from a previous lesson. We can use the 100 rule to find out that that x is going to be very, very small, and we can simply move things around and then solve for x, which gives us our hydroxide concentration. Once we know the hydroxide concentration, we can solve for pH, which is 9.87, and this, of course, comes from a pOH of 4.13. Remember, when you take the hydroxide concentration here, you have to solve for pOH. pOH equals the negative log of the hydroxide concentration. It's 4.13. 14 minus gives us the correct answer. There's a lot of steps there. You've seen it once. I would suggest that if you haven't actually worked through it yourself, get this off the screen, work through it yourself, and then check your work and make sure you have the correct answer. There's a couple pitfalls. People often fall into the 100 rule problem here, and they often stop at this point here. They see a pH looks reasonable. They're like, let's go, we're done. Well, no, we have a hydroxide. That means we're dealing with a pH that's going to be greater than 7. So give yourself a quick check on those kind of things to make sure you're on the right track. Any questions, let me know, and I look forward to talking to you.